This is the last lecture of the lateral equations. In this fifth lecture, we will look at the engine out case, which means one engine stopped working and what will happen. So what kind of maneuver or control the pilot need to conduct. Now let's take the case of the loss of the right engine. So since the right engine does not produce thrust, so the thrust only comes from the left engine. And however, you can see a D, that a drag from the right engine. That's because the engine is in a windmill condition, and then it will produce a drag. So that's counter to the thrust. Okay, and both of these thrust and a drag operate with a moment arm LE, so they have the same distance from the longitudinal axis. So in this case, in total, there will be a positive yawing moment produced, and this yawing moment will lead the aircraft to have a nose to the right condition. Okay, so because of the loss of the right engine, there will be a nose right yawing moment. And how do we correct this? If you're a pilot, you need to correct this, otherwise the aircraft won't track the right heading. So apparently we will have the rudder deflection. In order to correct the heading, and the rudder needs to have a positive deflection towards left, and this deflection delta R will produce negative yawing moment to counter the positive yawing moment due to the difference of T and D. Okay, so we can write down the moment equation, the yawing moment equation for the loss of right engine condition. So we have on the left hand side is yawing moment due to the T and the D, and the other hand on the right hand side, and there will be yawing moment due to the rudder deflection. Okay, so this is what we have. And we can find on the right hand side there is a v square. So let's assume if the v becomes smaller, so the aircraft is flying slower, then we require the aircraft will require larger rudder deflection angle, but the rudder has a limit, deflection has a limit, it can't be deflected unlimitedly, so we must to implement a minimum control speed. So this is what I want to say. There's a minimum control speed to allow the rudder deflection within a limit, within its limit, deflection limit. So let's read the text. Decrease of velocity v will require a larger rudder deflection. So it's based on the analysis of the yawing moment equation. But once the rudder deflection is at a limit, the restoring yawing moment could not correct the heading. So it won't be enough to correct the heading. So there will be a minimum control speed. So in order to correct the aircraft heading due to the loss of engine, so there is a minimum control speed needed. It can't be flying slower than that minimum control speed. Okay, so from the previous lesson, we know Cn delta R, that's the aerodynamic coefficient for yawing moment due to rudder deflection, is can be expressed as minus AR, that's the coefficient, and then it's VF bar is fin volume. So you can revise the look up the other slides and find this derivation. Okay, and then we can write delta R explicitly. So it's this relation. Okay, so now we get a question. When the rudder deflection angle becomes more critical, So under which condition the rotor deflection angle becomes more critical? Let's consider. So the answer is at low speed conditions, especially for takeoff or landing, because at those conditions, takeoff or landing, the airspeed of the aircraft is smaller, and then that produces a limit for the rotor deflection. And let's do a summary. Failure of the right engine results in a few things. Let's go one by one. First of all, we know there will be a positive yawing moment produced, and this is due to the thrust T from the active engine and the wind milling drag from the dead one, that's the right one in this case, and both acting on moment arm LE. So that will produce, in total, will produce a positive yawing moment. And in this case, because of this positive yawing moment, the aircraft will be guided nose to the right. So in that case, the wind is coming from the right wing, and that's according to the definition of side slip, that is a negative side slip. So there will be negative side slip angle, negative beta. So in this case, wind coming from the left side of the fuselage. Okay, because there is a negative side slip, and that will further produce the side force, and the side force is positive because it's pointing towards the right wing. So due to the side force on fin and the fuselage, that's a side force from the fin and the fuselage. And also there will be negative yawing moment. That's due to the weathercock effect, because the wind is from on the left side of the wing, on the fin, so that will produce a side force towards the right wing, towards the right, and that right side force will produce a negative yawing moment. Actually, it will counter the positive yawing moment produced by T and D. Okay, and we know the consequences. We have the positive yawing moment, negative yawing moment, and negative side slip angle, and also positive side slip force. And what if you are a pilot, what will you do to correct those forces? Okay, the corrections needed from the pilot. First of all, of course, as we discussed in the previous slide, and the pilot will deflect and the rotor to the left. So positive rotor deflection to produce a negative yawing moment. And also, because of the deflection of the rotor, the camber is increased. The camber of the fin, vertical tail will be increased, and that will produce a side force towards the right. So it's positive side force due to the rotor deflection. And simultaneously, a yawing moment due to rotor deflection will be produced, and that's a negative sign. So it will counteract the positive yawing moment due to the T and the D. Okay, so if we pay attention to the side force now, and both side forces are positive, and so far there is no negative side force produced. Then we have a question. The side forces are to the right, both side forces, and these forces will cause the aircraft to crab. So it will, the aircraft won't follow the right track. Is that right? So what will the pilot do? That's the question. So in order to answer that question, we need to have a rear view of the aircraft, and we can see the side forces, the positive side forces from the fuselage, and also from the vertical tail. So we can see both forces towards the right. Okay, the answer is the aircraft needs to bang to the left to introduce a side force to the left. Let's see how it happens. Okay, so this is what it happens. because of the bank angle phi, the total force of lift and weight will produce side force to the left, and that's negative side force to counteract the positive side forces due to side slip and the rudder deflection angle. Okay, so you may wonder, is there a limit? Because when an aircraft lost one engine, lost the power from one engine, and when a pilot do this kind of bank, remember it's not side slip, it's not bank turn, it's just a bank maneuver, and that will produce great discomfort to the passenger, also pilot. So according to the regulation, there is a limit to the bank angle phi. Usually it's within positive and negative 5 degrees. So it can't be too large, otherwise it's very discomfort. So this is for the engine out case. How do we analysis? And we use the right engine loss for the as example. So far we can conclude the lateral equations, and you can see we have a few static analysis and one dynamic analysis to understand the deflections of rudder and its consequences to the aircraft. Thank you.